Life moves fast, right? But sometimes one thought, one perspective can completely change the way we see the world. That's what this video is about, if it sparks even a single idea inside you. I'd love for you to like, share, and subscribe so we can keep this journey going together. Around 2 billion years ago, life plateaued in complexity and faced extinction. An event unfolded that would change the course of evolution. The first eukaryotic cell was born, a breakthrough in evolutionary history. This breakthrough opened endless new evolutionary paths for life. This may also explain why we haven't found aliens. Before diving deeper, we have 2 quick announcements. Stay tuned as we explore the impact of eukaryotes on Earth's history. We kicked off our first live stream with Dr. Matt Kaplan. Don't miss the unlisted link in our community tab. Join us on Patreon to ask questions. It's time to choose a side with our May merch. Will you maintain your own thermal equilibrium? Check out our Entropy Strikes Back design. Get yours today and support science. Join the resistance, signaling your opposition to entropy. These exclusive items will be available only in May. Do you suspect aliens are watching us? They could be in the government or just disgusted. But isn't it more rational to assume we're alone? Consider the null hypothesis of no aliens. The Milky Way galaxy is a big, empty place. Many potential places for life exist in the universe. Earth had a head start with life millions of years ago. Enrico Fermi posed a critical question in 1950. He asked, "Where is everybody in relation to extraterrestrial life?" The Milky Way contains over 10 billion Earth-like planets. Despite the vastness, we experience the silence of the cosmos. The reasons behind this silence remain unknown. Are aliens common? Our calculation might be oversimplified. What if there's a great filter? A barrier stopping civilizations? Some steps from a promising planet to civilization are improbable. Many civilizations may not make it past critical stages. Extinction or silence before revealing themselves could be common. The reality that most civilizations go extinct is scary. Could the great filter be ahead of us? We must ponder. Humanity has survived a brutal evolutionary gauntlet. We look towards a future unmarred by a statistical dead end. A great filter could lie in our past. This event is so improbable that it almost never happens. It could be the initial formation of simple life from a chemical soup, or a step in the transition from simple to complex life, eventually leading to intelligent life, like us. On Earth, life began surprisingly early in its history. This suggests a high probability that life could form under suitable conditions. We would expect longer timelines for life's origins otherwise. Simple life might be common throughout the universe. Organic molecules found on space rocks give us hope. There are tentative detections of biosignatures in exoplanet atmospheres. It took 3.5 billion years after life's start to reach humans. And now we have at most 1 billion years left before the warming of the sun renders Earth uninhabitable. If life formed late, we may have emerged just in time to watch the oceans evaporate. Maybe an early abiogenesis is necessary, even if it's a low-probability event. This is an idea from David Kipping and his Cool Worlds lab. David has a fantastic video on his channel. Let's pretend that simple life really is easy to form given the right conditions. Therefore, simple life could be common throughout the galaxy. If we want an early great filter, we should look elsewhere for the unlikely events. There are a few candidates for mass extinction events that could have wiped all life. Asteroids, extreme volcanism, and more keep hitting us. But life bounces back. The transition from unicellular to multicellular life might have been a colossal fluke. Most planets might be covered in slime molds instead of complex life. Yet multicellular life has evolved independently several times across the universe. The formation of the first eukaryote cell was a monumental event. This singular step paved the way for life's vast complexity. It marked the transition to multicellularity. Life became diverse enough to endure numerous catastrophes. Eukaryogenesis is considered a candidate for the Great Filter. A recent study highlights the significance of this event. This one event was truly game-changing for life on Earth. A freak accident of biology reveals why we don't see aliens. Over 2 billion years ago, two cataclysms struck our planet. The evolution of photosynthesis in cyanobacteria changed everything. Green slime, the first form of life, covered the Earth. Photosynthesis created oxygen, filling Earth's atmosphere for the first time. The Great Oxidation Event killed nearly all life. This may have triggered the next cataclysm, a massive glaciation event. Colossal stress once challenged early life forms on Earth. Single-celled organisms dominated, but survival was thin. A significant adaptation changed everything for life. A lone aran absorbed a bacterium, possibly for digestion. The bacterium not only survived, but thrived within the aran. This unexpected partnership provided vital benefits to the host. Such adaptations paved the way for complex life forms. The aeon was an anaerobic organism, avoiding oxygen as it was toxic to it. As atmospheric oxygen levels increased, the aeon struggled to survive. Contrasting this, the bacterium thrived in aerobic conditions, using oxygen efficiently. By incorporating the bacterium, the aeon gained new abilities and power. This partnership marked a revolution in energy production. Understanding this relationship helps unlock new possibilities in biology. Stay tuned as we explore the implications of this discovery. This begins with a symbiotic relationship between two life forms. Specifically, endosymbiosis occurs when one lives inside the other. Over generations, they exchanged genes and learned to replicate together. Eventually, they evolved into a single organism, the first eukaryotic cell. The bacterium shed genes and specialized in energy production. This journey led to the creation of mitochondria as we know today. Understanding this process is key to grasping the complexity of life. Survival in an oxygen-poisoned environment is crucial. Life was nearing the limit of adaptability to changes. Cells were reaching their complexity limits. Larger cells support more complex genomes. However, larger cells need more energy. The energy requirement increases with cell volume. Energy production relies on charge exchange. The energy produced relates to cell surface area. As cell size increases, energy needs rise significantly. Energy requirements increase by the cube of the radius. Energy production grows with the square of the radius. There's a maximum size a cell can reach before it struggles. Eukaryotes overcame this challenge by using mitochondria. Mitochondrial surface area allows for greater energy production. With their needs fully met, these bacteria focus on energy production. This leads to the growth of the complex eukaryote body and genome. Biologist Nick Lane calls this an evolutionary Big Bang. An unprecedented proliferation of new life forms follows eukaryogenesis. Lane refers to the formation of the first eukaryote as a black hole in biology. There's a hole in our understanding of evolutionary steps. This exploration seeks to bridge the gaps in the tree of life. The evolution of modern eukaryotes is complex and unclear. Which features developed before or after endosymbiosis? This uncertainty raises questions about their fundamental shifts. New research by Enrique Muro may illuminate these mysteries. Research indicates a computational crisis during early evolution. This crisis coincided with the Great Oxygenation event. Evolution's ability to adapt faced mounting challenges. And the solution to this issue coincided with the formation of the first Ugorote, a critical detail to why this event was so important. Here's a summary of the study on gene and protein length for over 6,500 species. They studied how gene and protein length correspond to species emergence on the evolutionary tree. This is a proxy for evolutionary advancement and complexity. For simple life forms, gene and protein length track each other. Over time, genes got longer and coded longer proteins. The longer the protein, the more possibilities for its mechanical function. For prokaryotes, almost all genes code for proteins. They're read off codon by codon to construct proteins amino acid by amino acid. These proteins fold into various forms to become the molecular machinery and genetic regulators. But as evolutionary time went on, a phase transition seems to have occurred. Genes continued to grow, but protein lengths capped out at around 500 amino acids. Why did protein length suddenly become decoupled from gene length? It seems that it was due to what the authors call an algorithmic phase transition. DNA was almost entirely used for protein coding. The development of complexity is linked to how quickly evolution finds new proteins. Finding a useful protein requires a specific amino acid sequence and proper folding. Protein folding is crucial for creating molecular machinery essential for life. The number of protein folding possibilities grows exponentially with length. As evolution explored proteins up to a few hundred amino acids, challenges arose. Continuing to uncover new proteins became computation-heavy and time-consuming. Finding new proteins requires longer evolutionary timeframes than before. New useful proteins emerged, but were they relevant? Research shows gene length continued to grow. What was this extra genetic material doing? Most DNA in complex life consists of non-coding sequences. These sequences play various roles in genetic function. There are regulatory elements to control gene expression. Introns help splice gene sequences flexibly. In a modern eukaryote, only a fraction of the genome codes for proteins. So what happened to allow this radical shift in gene function? Life found a new way to regulate protein transcription independent of proteins themselves. If DNA is a computer, life discovered a more efficient operating system. This led to a massive improvement in the search for useful proteins. It also improved how proteins are regulated and expressed. These changes revolutionized the biological landscape we see today. According to a study, an algorithmic phase shift occurred around 2 billion years ago. This shift coincided with the emergence of the eukaryotic cell. It marked the start of a rapid increase in biological complexity. We have a biosphere capped out in its ability to evolve. Cells have reached the maximum size due to energetic constraints. DNA has hit a limit in exploring new protein functions. This is where mitochondria integration plays a key role. The timing of these solutions remains unclear, but they are interconnected. At the last moment, Earth's atmosphere changed dramatically, rendering it unlivable for many organisms. This change coincided with the emergence of the first eukaryote, paving the way for survival adaptations. Adaptations opened doors to diversification, leading to enormous and complex cells. Soon after, the first multicellular organisms appeared, marking a significant evolutionary step. Another endosymbiotic event added cyanobacteria, giving rise to photosynthesizing plants. These plants played a crucial role in stabilizing the atmosphere and supporting life. Thus, the journey from eukaryote to complex ecosystems reshaped our planet. The phenomenon of eukaryogenesis may reveal deeper truths. Endosymbiosis and algorithmic phase transitions may happen under stress. We ponder whether these transitions were gradual or a cosmic fluke. This uncertainty is akin to a black hole surrounding our understanding. Incremental steps or a singular event. What truly happened? If it's a fluke, eukaryonesis may represent a great filter. The implications of such a transition could redefine our understanding. In a vast universe, habitable planets host simple life forms that thrive. These life forms grow and transform their environment, altering atmospheres. Unfortunately, many face extinction after drastically changing their climates. Others may adapt to new conditions, reaching a state of dull equilibrium. Imagine galaxies filled with simple slime worlds and fossilized algae beds. If this is our reality, we may find solace in knowing a crisis may have passed. Perhaps the dire fate of others is a chapter we can leave behind. Our future lies in our hands, not just statistics. Thanks to Novium for supporting PBS. Introducing the Novium Hover Pen Interstellar, a unique gift. Available in Space Black, Starlight Silver, Mars Magma, and Neptune Blue. It's refillable and designed for convenience, featuring a meteorite fragment embedded in the Black Edition. Also available as Novium Future, a 2-in-1 fountain and rollerball pen,